Hi, this is Shyamala Gauri, Assistant Professor in CSE Department, Rohini College of Engineering and Technology. CGS 355 Neural Networks and Deep Learning. Unit 4 Deep Feed Forward Networks. The topics covered in this presentation is a probabilistic theory of deep networks. Its key concepts and its benefits are explained. Introduction. A probabilistic theory of deep learning aims to integrate principles from probability theory and statistics into the deep learning framework. This, this theory provides a formal and probabilistic perspective on how neural networks, particularly deep networks, operate and learn from data. It interprets the predictions and parameters of deep learning models as distributions and uncertainties rather than fixed values, thus allowing a more flexible, interpretable, and theoretically grounded approach to understanding deep learning. Key concepts. Probabilistic models. In probabilistic deep learning, a model is viewed as probabilistic process. Instead of trying to directly predict a single point estimate, the model predicts a probability distribution over possible outcomes. This allows the model to represent uncertainty in its predictions. Number 2. Bayesian neural networks. A prominent example of applying probabilistic principles to deep learning is the use of Bayesian neural networks. BNNs treat the weights and biases of a neural network as probability distributions rather than fixed values. This means instead of finding a single point estimate for each weight during training, BNNs seek to estimate the distribution over possible weight configurations. The network is trained not only to make accurate predictions but also to quantify the uncertainty in its predictions by integrating overall possible weight configurations. This uncertainty is crucial in tasks where knowing the level of confidence in a prediction is important. Latent variables and variational inference. In deep learning, especially in generative models like variational autoencoders or generative adversarial networks, probabilistic models often assume that the observed data is generated by some underlying latent variables. Variational inference is used to approximate the true posterior distribution over the latent variables since the exact posterior is often intractable to compute. In practice, variational inference optimizes on approximation of the posterior to make the inference computationally feasible. Likelihood function. A central concept in probabilistic deep learning is the likelihood function, which is a measure of how likely the observed data is given a set of model parameters. For example, in a classification problem, the likelihood function might represent the probability of the observed labels given the model's parameters. This is typically maximized during training to find the model parameters that best explain the data. Uncertainty and overfitting. One of the key benefits of a probabilistic approach is the ability to model uncertainty. A typical neural network model may give point estimates, but in a probabilistic model, predictions come with associated confidence levels. Bayesian neural networks provide uncertainty estimates about the model parameters and predictions, which can help avoid overfitting. This is because rather than learning a deterministic mapping from input to output, the model learns a distribution over possible functions, reflecting uncertainty and preventing the network from fitting noise in the data. Markov chain Monte Carlo and sampling. To estimate the posterior distribution of the model parameters in Bayesian neural networks, techniques like Markov chain Monte Carlo are often employed. MCMC methods generate samples from the posterior distribution by constructing a sequence of correlated random variables. This allows the model to approximate the true distribution of weights. In practice, exact Bayesian inference is often computationally expensive, so methods like stochastic variational inference or Monte Carlo dropout are used as approximations. Dropout as approximate Bayesian inference. A simple but insightful probabilistic interpretation of dropout is that It can be seen as performing approximate Bayesian inference. In standard dropout, randomly selected neurons are dropped during training, which forces the network to learn robust features that don't depend too much on any single neuron. This random dropping can be interpreted as placing a Bernoulli distribution over the activation of each neuron during training, which leads to a probabilistic interpretation of the network's behavior. During inference, dropout is turned off and the network is effectively averaging over many possible neural network configurations. Probabilistic generative models. In generative tasks, deep learning models like variational autoencoders or Bayesian neural networks are used to generate new data by sampling from a latent space where the latent variables are treated as probabilistic entities. These models learn to model the probability distribution of the data. A VAE, for instance, learns a latent space where points are sampled from a probabilistic distribution and these samples are decoded into generated data. The benefits of probabilistic theory are uncertainty estimation, better generalization, interpretable predictions, and improved handling of small data. Thank you.